Welcome back to Business Mathematics 1. I am Eric from Mathematics Study Program, Faculty of Mathematics and Natural Sciences ITB. So for today, we are going to discuss additional applications of the derivative, especially we will look into increasing and decreasing function and relative extrema. So for the first one, we will going to review on inequalities, solving inequalities. The first one, we have to find all x in real such that it satisfies this inequation. We divide by 2 and we have this, factor it out, and we can draw the diagram of sign. This is less than 0, so minus 2 and 2 is not included. And by the intermediate value theorem, we know that the sign can only change at minus 2 and 2. So by testing one point between minus 2 and 2 and on the left of minus 2, on the right and 2, we have this plus minus plus. And all x in real that satisfy is given by this set or this, using this interval notation. And the second one, find all x in real such that it satisfies this. This is less than or equal. So if we draw the diagram, the sign diagram, minus 2 is included, 1 is included, 3 is included, but minus 1 is not included because it is not in the domain of this function. Yeah, and we can test points, and we have minus is on interval minus 2 and between minus 2 and minus 1, but minus 1 is not included. Okay, yeah. Now let's start our discussion concerning increasing and decreasing function. So this is the graph of increasing function, and this is the graph of decreasing function. So function fx is increasing or decreasing at interval e is by definition is if for every x1 less than x2, that is this x1 less than x2, we have the height is less than the height at x2. Yeah, the height I mean is the value of f at x1. Okay, the height is less than the height at x2, and the same for the decreasing function. We can use the slope of the tangent line of graph y equals fx at x to know whether a function is decreasing or increasing if we know the derivative. And this is the relation between monotonicity and differentiability. Let f be a differentiable function at interval I. Then if f prime x, the derivative of f at x is greater than 0 in I, then f is increasing. Okay, yeah, the same when for the decreasing case. Okay, here is the example. Find the interval of increase and decrease for the function given, or find the monotonicity for the function this. And we want to find the zeros of this. F prime x is this, and we can factor out 6. Factorize this one. I can factor this out, so I have this. So the zeros is given by minus 2 and 1. And I can, to find the interval of monotonicity, I have to find the sign of f prime, and the zeros is given by minus 2 and 1. So I can, using test on some points in here, and we have plus minus plus. It means by the previous theorem, this is increasing, decreasing, increasing. So the function f is increasing at this interval, union with this interval, and decreasing at this interval. Okay, yeah. From here, I think you can guess what is the local minimum and local maximum. Yeah, this is local maximum. Yeah, local near minus 2. Okay, yeah. This is local minimum, local just near 1. Okay, yeah. Now we will look at the local maximum and minimum. One application of derivative is finding the relative maxima and minima of a function. By the way, maxima and minima is the plural form of maximum and minimum. This is the definition of relative maximum and minimum. Graph y equals fx have relative maximum at x equals c if fx is less than fc in an interval x A, B containing C. So this x equals C, the graph of this function have maximum at x equals C. Why? Because at this neighborhood, maybe this is A, this is B, and in interval, it is the highest. Fx is less than of Fc. So Fc is the highest. Compared with Fx around this neighborhood of C. The same, this is the lowest. Fc is the lowest. So this is the minimum. This is not a maximum and minimum. Why? Because on the left, this is not the minimum. On the right, this is not a maximum. Okay, we can do the same game for this one. What's the difference is at here, the derivative of f at c is not defined. This one also, and this one also. But in this case, the derivative is defined at x equals c. Okay, so this point we usually call x equals c. This point we usually call a singular point. Okay, in later discussion. Okay, so finding relative maximum or minimum is hard, but if the function is differentiable, it's another story. So this is the relation between differentiability and the local maximum and minimum. So if f is differentiable everywhere, then x equals c is called a stationary point of f. If f prime c equals 0, so the function f can only have a local maximum or minimum at x equals c. Oh, sorry, f can have a local. Okay, that's right. Yeah. Okay, now we can find local extremum, maximum or minimum by finding the stationary point. Okay, this one, if I have this is increasing and decreasing, by looking at the sign of f prime, we know that this is the maximum. And this one, the minimum. But what about this one? This is I don't know. So this is not a maximum or a minimum. This one also, this is not a maximum or minimum. So how can we differ this? By looking at the derivative near C. Okay, so in the textbook, C is defined as a critical number if it is either a stationary point or a singular point. Singular point, remember, when f prime c doesn't exist. Okay, the point c, fc is called the critical point of fx. Okay, and relative extrema can only occur at critical point. Don't forget, critical point consists of stationary point and singular points. Okay. Okay, example of local extrema. Determine the relative maximum and minimum of this function. We know this is a polynomial function, so the derivative is always the first derivative is always exists. So we don't have singular point here. So first of all, if I want to find the relative maximum and minimum, I have to find the monotonicity. I want to find the zeros of f prime x first. This is the f prime. I can factor out x, and I can factorize this, and it will become this. So the d zeros is given by 0 and -3. Okay, yeah, the stationary point. What about the interval of monotonicity? I can draw this -3 and 0. This is decreasing, decreasing, increasing. So we know that this is not a maximum, this is not a minimum, but this is a minimum. Okay, yeah. We usually call this is the first derivative test. Yeah. So based on the first derivative diagram above, function f doesn't have relative maximum and doesn't have relative minimum at x equals 0, but have relative minimum at x equal 0. Oh, it doesn't have relative. Oh, this is right, yeah, with minimum value -8. Okay, so this is the discussion about increasing and decreasing function and local extrema. Next, we will discuss about the concavity of a function. Thank you.